Mobile messaging architecture feels like absolute magic when it works. But let's be real, it's a total black box for a lot of engineers out there. So in today's explainer, our goal is to completely demystify the robust architecture behind iOS push notifications. We're literally going to follow the exact journey of a single message from a server way out in the cloud all the way to a user's lock screen.
Now, the fundamental question that drives this entire architectural requirement is just this: how do you reach a user when their app is completely turned off? Think about it. If a user force closes your app or the operating system just puts it to sleep to save battery, your application is functionally dead to the network. You have absolutely no direct way to send them a chat message, a breaking news alert, or a trading update. This massive communication gap is exactly why specialized push notifications are an absolute necessity in modern system design.
To figure this out, here's our roadmap. We'll start with the offline communication gap, then move into a push architecture overview. After that, we'll cover device registration and tokens, how to handle iOS app states, and we'll wrap up with delivery challenges and limits.
Okay, Section 1, the offline communication gap. Let's look at the exact limitations of standard network protocols in a mobile environment.
So, when your app is actively running, you're likely using a WebSocket. This is a persistent, bidirectional, full duplex channel over a single TCP connection, which is absolutely ideal for real-time updates. It's the industry standard, used by massive companies like Slack. But here's the catch. Mobile operating systems are absolutely ruthless about battery life. The very second your user swipes up to background that app, the OS is going to step in and eventually kill that connection.
And that brings us to the dilemma. The app is asleep, the connection is dead, but the message, it still has to arrive. You can't just wait around for the user to open the app again to show them a message from 3 hours ago, right? That specific constraint right there is what sets the stage for needing a specialized, out-of-band delivery mechanism.
Which brings us right into Section 2, the push architecture overview. Let's reveal the ultimate middleman that bridges this gap.
To build this middleman, we have to navigate a pretty clear platform divide. Android relies on Firebase Cloud Messaging, while Apple uses the Apple Push Notification Service, or APNs for short, which is handled via the UN User Notification Center delegate. Because these workflows are so distinct, we're going to focus strictly on the iOS implementation and Apple's infrastructure today.
Now, Apple implemented a brilliant architectural solution here. Instead of letting 50 different apps maintain 50 different battery-draining background connections, the iOS device itself maintains one single, low-power, persistent TLS-encrypted TCP connection directly to APNS servers. It's kind of like APNS is the ultimate global post office. Individual apps don't manage their own connections when they're asleep. They delegate the whole shebang to the iOS system, which just quietly listens on this single, highly efficient connection for any incoming mail.
All right, Section 3, device registration and tokens. How does a device actually get an address in this specialized postal route?
Well, it all kicks off with a background handshake during app installation. Here's the exact flow. Step 1, the device registers with APNs in the background. Step 2, APNs issues a unique device token identifying that specific installation. Step 3, the iOS app securely sends this token to your backend. And Step 4, your backend stores a mapping between the user ID and this specific device token. This mapping is absolutely crucial because your backend needs to know exactly where to route future alerts when that user's WebSocket connection inevitably drops.
So let's look at the moment of action. A message arrives at your backend for user, but they don't have an active WebSocket connection. What actually happens? Well, your backend triggers a push notification by sending an HTTPS request directly to the external APNs provider. This request includes the specific push payload, like the actual text of a chat message, along with that user's unique device token. Essentially, your backend is handing the message to Apple's post office and saying, hey, please deliver this to the exact device holding this token.
Let's move to Section 4, handling iOS app states. We are transitioning to the client side now to see what happens the second Apple pushes that data down to the device.
What's really fascinating here is how iOS branches its behavior based entirely on whether the app is awake or asleep. If the app happens to be in the foreground, the push notification goes directly to the UN User Notification Center delegate. The app can process the payload silently without necessarily showing a lock screen alert, which lets it sync data instantly. But if the app is in the background or totally terminated, the OS takes over completely and displays the notification directly in the system tray. The app itself is completely bypassed at this stage just to save resources.
So how does the app finally get the data? This is the climax of our message's journey.
When the notification is just sitting there on the lock screen, your app is still fast asleep. But the exact moment the user taps that system tray alert, the operating system springs into action. It forces the app to wake up and move to the foreground. Once it's awake, the app's push notification client is finally handed the notification payload by the OS. It can then read the data, trigger a back-end sync, and display that relevant conversation right to the user. And finally, Section 5, Delivery Challenges and Limits. Because up until now, this probably sounds like a flawless system. But we have to introduce the brutal reality of mobile system design.
The reality is that push notifications are never actually guaranteed. System engineers face some massive hurdles here. First off, Apple will actually throttle notifications if the device is in a battery-saving mode, which can delay delivery or batch requests together. Second, you have strict payload size limits. You definitely can't send megabytes of data through APNs. Third, users can simply deny permissions or opt out, completely severing this communication channel. And fourth, if you want a notification to open a specific screen in your app, you have to implement complex deep linking via URL schemes, and that can be incredibly tricky to restore if the app wasn't already running in the background.
To give you a sense of the staggering architectural scale required to manage all this, just look at Slack. Their server-side infrastructure decides exactly when and what to push. Every single message goes through an event pipeline, and Slack's job queue system processes over 1 billion jobs per day, including the fan-out of push notifications. They literally enqueue background jobs just to handle routing these real-time alerts across APNs and FCM at an unimaginable scale.
But you have to remember, this entire system is incredibly ephemeral. If a device is offline, APNs queues the notification, sure. But those queued messages are eventually dropped by Apple's servers if they remain undeliverable for too long. Because of this, and all the throttling and opt-outs we just discussed, push notifications serve as a great lightweight alert mechanism, but they absolutely cannot act as the single source of truth for a resilient application.
Which leaves us with this final provocative thought. If Apple might throttle your message, and if push notifications simply aren't guaranteed, what is your system's backup plan? How does your app ensure data integrity and synchronization the very next time it connects to the internet? It's a massive puzzle in offline-first architectures. Think deeply about that as you build your next mobile system. Keep learning, keep designing, and I'll catch you in the next explainer.